Okay, let's get started. You're gonna continue to talk about recurrent neural networks today. So today is the deadline for programming assignment 3. So make sure to do that. I'm gonna release the next assignment tomorrow morning. So we need to start working on RNNs because this is the last lecture on RNNs. And speaking about that, we were talking about sequential problems in AI, especially in natural language processing. And then we saw how recurrent neural networks can be used to solve these sequential problems or to model data that is sequential. And then we saw how to do the forward pass in RNN, and I finished the lecture talking about the structure of backward pass, right? We do a backpropagation through time. So we saw that we have to train our weights over time, and we can do that either processing the whole sequence if you have enough hardware to do that, or we can do that in a truncated way if we can't, or if our sequences are too long. And the plan for today is to keep talking about backpropagation. We're going to see the equations to do backprop with RNNs. And then I'm going to show you a very compact implementation of a simple RNN. Hopefully, I think the goal here is to show you that even though they might look scary, it's not that hard to implement an RNN from scratch. And then I'm going to discuss from that implementation this problem of vanishing and exploding gradients in RNNs. And then show some alternative architectures that we can use to deal with that problem, particularly LSTMs and GRUs. And then we're going to see how to combine or how to process sequences from both from left to right and right to left, and how to combine those and form what we call a bidirectional RNN. So last time we were talking about RNNs, and this is the forward pass of the RNN, right? We define it by these two equations. We first update our hidden state edge of T. We're using two matrices, right? The WX and W edge. And then we use the hidden state vector edge T to produce an output for each time step T, okay? And then we saw that we can build many different variations of RNNs using that same formulation, right? Formally, you can do many to many, many to many, but in this sequence-to-sequence structure, where our input has a different length than our output, we can also have many to one, and one to many, and one to one, okay? So this is a recap of what we were doing last lecture. So today I'm going to actually talk about RNNs through the lenses of this application, or language modeling. So a language model is a fundamental problem in natural language processing, okay? Similarly to how maybe image recognition is a fundamental task in computer vision, this problem of predicting the next word, or a character if you want, from a textual context is fundamental in natural language processing. And what is this problem? So here's a sentence, right? This lecture is so if I asked you to complete this sentence, what word would you pick?
Hard.
Sorry?
Hard.
Hard? Yeah, it's okay. It's a good guess. Anybody else? Easy. Okay, also nice, yeah. Well, it could be cool, it could be interesting, right? But it could be many other adjectives. But we wouldn't likely complete this sentence with classroom or university, even though these words are somehow related to lectures, right? They're not good guesses to that word. And we know how to do that because the way we learn grammars, the way we learn languages, right? But what is important here is that there is a context that is fundamental for us to guess that word, okay? So we're going to call these 4 words here a context, and I'm going to formulate them as x1, x2, x3, and x4. So this is a sequence of words, right? And what a language model does is it models this probability, or particularly this conditional probability, right? We want to, when we guess, actually, what we have in our brains is somehow the probability of the fifth word given these last four words. Right? So that's how you would write this conditional probability using probability notation. And here, at the bottom, you would have all the possible words in the dictionary, right? We don't actually do that in our brains. We are smarter than that. But if you're trying to make a computer program that models that probability, that program would probably have to list all the possible words and give higher probabilities to the words that are more likely in this context and lower probabilities to the words that are less likely in this context. Right? So you would have perhaps 200,000 words there, all the words that you can find in the dictionary, and just the correct one should have high probability. So if you sum all the probabilities in these rows here, it should sum up to 1, okay? By definition of probability distribution, okay? And this problem of predicting the next word, giving a context, it's called language modeling, and it's fundamental in natural language processing. And I'm going to give you some examples of why. First of all, you could build these interesting applications with it, right? For example, every one of us who has a cell phone, we have, when you're typing on your keyboard suggests like the top 3 words that comes next, right? What you have in your keyboard is a language model. It predicts the next word giving the previous context, okay? So perhaps not as intuitive as the previous one. You need language models to do speech recognition. Because let's say if someone says a sentence, right? And that sentence is the apple and pear salad. Right? You just get the sound of that. How would you know that the person said the first or the second sentence? Right? By the other words, right? It's the only way to say, because pear and pear, they have the same sound. But one is correct and one is wrong in this context. So you can use a language model to compute the probability of the whole sentence. Okay? So that sentence should, if your language model is well trained, it should give a lower probability to that sentence than to the first sentence than to the second. Okay? Then you can when you're decoding this audio, you can say, okay, I could figure out which word there maximizes the probability of that sentence, okay? So there's many other applications of language models. And as you probably know, I should have translated this slide, but as you probably know, ChatGPT is also a language model. It's just a large language model, but it's the same idea, right? It predicts the next word in the sequence, but it does that the same way, but it was trained in a very large data set. Okay? When I say very, I'm talking about the entire internet. So it's really surprising that ChatGPT can write code, can create slides, can make diagrams, or can do all sorts of things just by predicting the next word. Okay? But anyways, how would you train a language model, right? So, well, ideally you should get a very large volume of text, and then you have to create these examples or these pairs x, y, right, in the following way. So consider you go to Wikipedia, for example, and you download the entire Wikipedia. And eventually there will be an article there about the Universidade de Viçosa, or UFV. So what you would do to make a data set for this problem, you would create a window, and I'm assuming here a window of size 8. And you would slide that window over the document, and you see these windows are highlighted there on the document. And then for each of these windows, you would make the X, or your input, the first 7 words, and then your output would be the next 7. So consider the window, that very first window there. So this is our context window. Okay, I'm assuming j equals to 8. So you would have this sentence. So this is our context window. And what you're going to do is, I'm going to make an input and an output. And to build my input, I'm going to pick all the words from 0 to 0, 1, 2, 3, 4, 5, 6, right? So 0 to 6. And this is going to be my X. This would be Universidade. And then note how I'm going to shift this window by 1 to get the Y. So the Y for this X would be Universidade, Federal, so on, as you see on the slides. Okay. So the goal here is to predict the word Universidade from the word A. And then I want to predict the word Federal from the sentence A Universidade. And then I want to predict the word de from the sentence A Universidade Federal, and so on and so forth. So the way you read this table is like this. A Universidade Federal, A Universidade Federal de, A Universidade Federal de Viçosa, and so on and so forth. So you don't have to explicitly build all the possible prefixes and suffixes in this table. You can write it this way, and then we can use this structure to actually learn all prefixes in this table. Okay, so that's how you would make this data set. Okay, question. So something that I haven't talked about till now is how to represent words as vectors. We've been talking about RNNs and words and sentences, but how do you actually put these on the computer? How do you actually represent these words, right? We know that we normally represent characters as like using a table in computers. We use ASCII or some other type of standard. But in machine learning, we're going to do something different. We're going to represent words with vectors, okay? And let's assume this example. Lucas is a professor, which is a sentence that could be inside maybe a Wikipedia document somewhere about UFV. But one of the simplest strategies we can use to represent words, not works, but words as vectors is what we call one-hot encoding. And to do that, what we do is we assign an index k for each word in a vocabulary. So first of all, we have to define what is our vocabulary. And I went online and grabbed a text version of the English dictionary, and I found this one that has 466,000 words approximately. So the very first word there is the word A, which is like the article A, and then you have all the words with A, and then B, and then C, so on, the same way you have in the dictionary, until all the words with Z, and then maybe the last one would be Zulu or something. So you would have this very large vector, which almost 500K dimensions. And each dimension is a feature, okay? So each word is going to be represented by a feature vector where, so only the kth feature is 1 and all the other features are 0. So it's a very sparse vector which has only a single value 1. And that value 1 goes in the index k of that word in the vocabulary. Okay? So for instance, the word Lucas would be this vector full of zeros with the value 1 for the dimension 223,061. Okay? And similarly, you would have the word is with a vector full of zeros, and the 1 would be in that dimension, 198,015. Okay? And same for the word A, it's easier, right? It's the first word in the vocabulary, so it would have 1 in the first dimension and 0 in all the others, okay? And that would be able to represent every word in the vocabulary. It seems very inefficient to say the least, right? But that's the simplest thing we can think about. And one key feature that is interesting about one-hot encoding is that the distance between any two vectors is the same. So there is no relationship in terms of distance here, okay? So this type of encoding is very useful when you have categorical problems, especially when your categories don't have a relationship to each other. They are just different categories of something, okay? And the first approach we're going to try with words is using one-hot encoding. And there is a whole subfield of natural language processing, or a key problem in natural language processing is how to represent words with vectors. That's actually a research topic that people have been studying for a long time. Because, for example, if you think about this a little bit deeply, wouldn't it be nice if you came up with an encoding where words that have similar meaning have maybe similar, or are located in the similar location of a space, right? So, for example, the word car and motorbike are somehow closer in this vector space, and maybe king and queen are also similar in this space because they are maybe part of the royal family, or maybe they appear in the chess game or something. So it would be really nice to group words that somehow have similar meaning or context in maybe a closer location in a high-dimensional space. We are not doing that yet. We're going to see that actually next lecture. But yeah, this is a very simple solution for now. And just keep in mind that every vector is going to have, or every word is going to have that very same dimension, 466,549. Let me just show you. I actually got this from here. Where is it? Yeah. So this is the file I found, which has all the words in the English dictionary. So you would have all the words with A, and then, so it's a very large file. Then D, G, blah, blah, L, and so on, until the words with Z's. Okay, so let's run an example now of a language model. Now that we know how to do a forward pass with RNNs, we also know how to represent words with vectors. And I'm going to pick that very simple sentence. Lucas is a professor. I'm actually made it even smaller, so it fits on the slide. So our goal in the language model is to predict the next word given the previous words. So I have at the bottom my input, which would be Lucas is A. And I'm finishing here at the time step 3 because there's nothing after professor, right? So, and this is how you would do a forward pass for that example. So first you would start with x1. But before that, we have to initialize our h0, our hidden state. And we initialize it with zeros. And I'm picking here the size of the hidden state as 3. This is a hyperparameter. I decided to pick it with 3 dimensions only. So they are all zeros. Okay? So we first update the edge state, and I'm showing that when I'm showing in green here is a possible result. I did this by hand, so I actually didn't, the math might not be right, okay? But it doesn't matter. What matters here is like how these numbers would play out a little bit. So on green now, you see the updated edge. That would be h1. And then we would use this h1 to generate our first output, y hat 1. And now, that vector has 4 dimensions because in order to make this fit on the slide again, I couldn't use those 500K dimensions. It wouldn't fit here, right? So I'm just shrinking it to 4. So you see, imagine that there is only 4 words in the vocabulary. If there were only 4 words, then maybe the word Lucas would be the third, the word is would be the second, the word A would be the first, and professor would be the last one, okay, just to simplify the problem. So what the output layer produces at each time step is a probability distribution over the vocabulary. So what you see here is 0.1 is the probability of the word A. And it says like, oh, the probability is 0.1 at this point, okay? And then the probability of the word is 0.4. The probability of the word Lucas is 0.2. And the probability of the word professor is 0.3. Okay? So then we are now on time step 2, and we're going to send the edge 1 from the previous time step to the second time step to compute the edge 2, which is 1, 0, 3, minus 0.1. These are arbitrary numbers. Okay? But this edge 2 would be used then to produce an output, and if you want to see the equations, they are here on the right. Okay? So the way we compute the outputs. So edge 2 would be also a probability distribution. Note the softmax activation function I'm using here, right? So that is going to make a probability distribution over the vocabulary. Now, what that distribution is saying is that, oh, now the model thinks that there is 0.9 probability for the word A, 0 probability for the word is, 0.1 probability for the word Lucas, and 0 probability for the word professor. Okay? And then I would do the same for the third time step. Now, hopefully you got the idea, right? I also have a probability distribution. And that's the end of the forward pass. So we do have a probability distribution for each time step. Okay? And we computed them sharing the same 3 matrices. We haven't updated the weight matrices yet. They're the same. Okay? This is the forward pass. There's no update yet. So how do you compute the loss for this model? So you're going to use categorical cross entropy, okay, which is written there, which is y a log y hat a, or sorry, I. So it's the sum from j going from 1 to d, right? And that first summation there, the inner sum, right, that is over the dimensions of the vocabulary, okay? So that's the d. D is equal to 4 here. I have 4 possible words, okay? That external sum that goes from 1 to t, right, that's the sum over the time steps. I have 3 time steps here, okay? So I'm going to sum, for each time step, I'm going to sum the error for each word. Okay? And what I'm showing there on the right next to the blue boxes, you see the ground truth distribution for each time step. So what I wanted to achieve was y1 equals to 0, 1, 0, 0. But my model outputted 0.1, 0.4, 0.2, and 0.3 in the first time step. In the second time step, the ground truth is the word A. I want to predict the word A, right? Which is 1, 0, 0, 0. And my model predicted 0.9, 0, 0.1, 0. And on the third time step, the ground truth word is professor. Note how I want to predict is after Lucas. And after Lucas is, I want to predict A. And after Lucas is A, I want to predict professor. Okay? So this way I'm training my model to predict the next word. Okay, for any given prefix in this sentence. Okay? So let me just simplify a little bit this loss function. Because if you pay attention, we can actually eliminate that first, the inner summation. Because we have a one-hot encoding vector. So there's only one dimension, k, which would be a value different than 0. Right? If I'm summing here, what I had here before was this number times this number, or actually, this number times the log of this number. But because this is 0, the whole thing, the multiplication is 0. This times the log of this is 0. This times the log of this is 0. So there is only one value on the one-hot encoding, which is 1. Okay? And I'm denoting that k. So there's only, I can remove that whole summation there and just work with the dimension where my ground truth has k equal to 1. And we can simplify it further because yk of I is 1, so I don't need that term there. Okay, and then something I want to show, you would get a value for a loss for each time step. And I'm assuming that, again, that math is not right. Don't try to do it at home. You won't probably work. But what I point out is that look at how the distribution on the time step 1 is more confused. So the model is given, so it's distributing the probabilities more equally. Right? There is one dimension with 0.1, the other one 0.4, 0.2 is 0.3. So it's more like it's closer to a uniform distribution. It's not a uniform distribution, but it's closer to 1. Right? And so the value would be 35, for example, 0.35. But if you had, on the other hand, a distribution that I'm showing now on the second time step, right? Note how this distribution is more or less confused, right? It has more certainty about which word should come now. It's giving 0.9 probability to the correct word, okay? So then the loss would be 0.04, so it's a much lower loss than the first case, okay? And here is kind of in between, right? So you would have a loss of 0.12, for example. Right? You have that probability 0.7 there, but you also have 0.2 and 0.1, so it's a skewed distribution, but there is a 70% chance of predicting the correct word. So the loss would be in between 0.04 and 0.35, okay? So that's how a language model would play out. And then you can run back propagation now because you have losses. And then you adjust the weights. And you do that again and again and again, and eventually your model will learn to predict the next word, okay? One thing to keep in mind is that note that we have to compute the loss for a certain time step, we have to sum from 1 to that time step. So the loss of the first time step is just that 0.35. But the loss of the second time step is 0.35 plus 0.04. And the loss for the third time step is 0.35 plus 0.04 plus 0.12. So first time step, you are summing up to that time step to compute the loss. Okay? Because what we want is the model, we want the model to not get an individual probability right, but you want to get all, to correct that time step and all the other ones before, right? So that's why we are summing. So the loss of the time step 2 depends on the loss of the time step 1. The loss of the time step 3 depends on 2 and 1, and so on and so forth, okay? All right, so bear with me now. We're going to do backprop for RNNs. So what I'm showing here is the computational graph of the forward pass for the first time step. So here you have as input x1. You have also as input the W edge, WR, and B edge weights, okay? So the only thing we are doing differently here, we are using this node to do the linear part of the hidden layer. And then a second node, tanh, to compute the activation or the non-linear activation. And then you have the output layer are the next following two nodes, right? Again, we are separating now the linear part from the non-linear part. And then at the end, you compute the loss for the first time step. And we're going to do that for every time step. So here I'm using 3 as an example. Okay? It's the same idea. Now I'm just showing you this rounded nodes, so you see this as a computational graph, and it's very useful to separate the linearity from the non-linearity when we are doing backprop, especially when we're deriving the loss, the partial derivatives. Okay, so I don't want to spend too much time talking about this, but I just want to show you how you would apply the backpropagation algorithm on an RNN. And we've seen this, right? It's the same algorithm. We start with the base case, which is always 1, which is the partial derivative of L with respect to itself. The second step, we're going to apply now the chain rule. We're going to multiply the result of the first iteration, which is dl dl, multiplied by dl dy hat t, right? Just applying the chain rule here. Remember, we are flowing the gradients from the top to the bottom, so now I have to apply the chain rule once, and I'm going to need that local gradient there, dl dy hat t, right? That gradient we're going to need to compute ourselves. That's the local gradient, which is defined this way. I'm giving you the formulas, okay? So you could implement this if you wanted. And now I keep applying the chain rule. It's all the chain rule, right? So now my third step would be to compute dl dz here, okay? Which is, again, chain rule here. So I'm going to use this partial derivative is going to be here, right? And then I have to multiply that by the local gradient, which is dy hat t over dz yt. Since it's a local gradient, I need to I have to build it inside the node. Okay. Again, chain rule. But now I have chain rule for each of these 3 inputs here: dl dby, dl dyyy, and dl d edge t. Again, chain rule, right? So if you look here, this partial derivative is this one, and this one comes from here, and this one comes from here. So I just need these 3 local gradients. This one, dzy, dy, dwyt, dzyt, d edge t, and dzyt, dbyt. And this one we actually already know. If you remember from the backpropagation lecture, these are the same local gradients, okay? Because this is a linear node. We actually have seen this node already, right? It is just a linear node, so we already know how to compute the partial derivatives of these nodes. And now, 7th step is, again, we're going down, right? So chain rule again. This partial derivative here comes from here, right? And now I need this local gradient d edge t, dz edge t, which is this, okay? And now I'm at the end. I need 3 more updates, right? Again, chain rule. So this partial derivative here is this. This one is this here. This one is this here that we compute. Oh, sorry. This one is this here from 7th step. So we are already reusing the partial derivative from the previous step, okay? And we combine that with the local gradients, and the local gradients are very similar. This is also a linear node. It just happens to have an extra term there, but we already know how to compute derivatives of linear nodes. So that's your local gradients. If you're using these equations, you can actually implement backprop by hand on RNNs. Okay? There's only one thing missing here, which is this arrow right here, okay, which would be your 11th step, okay, which is the gradient flowing through the RNN through the time steps. So here, imagine this is the 3rd time step. This arrow is going now to time step 2. And then you do the same thing again for that time step. and again and again and again. So you start from the back, so you start at the very last word in your sentence, and you flow the gradient backwards on time. As we saw on the slides, or I showed you that we do that. We first compute the forward pass on time, or over time, sorry, and then we back propagate over time backwards, right? And just for your reference, I actually already simplified the equations for you. So if you want to look at this slide and make sense of the backprop, you could. I'm not going to discuss this because we don't have time. I want to show you it in code. So this is a very famous implementation of a minimal RNN by Andrei Karpathy. We have been talking about him in this course a lot. But this is a very popular implementation of an RNN because it has, you can't see it, but it has only 112 lines of code. And he's doing everything in NumPy here, literally from scratch, no PyTorch, okay? So all the forward pass, backward pass, parameter initialization, data set creation, everything is here. Okay? And there's still comments, so it's not a very compact code. So I want to show you this because it's a very educational implementation, I think. And this works. You can actually get this, just download this single file, grab a data set of plain text, any file you want, and then you run this and it's going to work. It's going to start training the network, and then it generates text. So this RNN is trained as a language model. And so it predicts the next character in a sentence. It's not predicting the next word, okay? So it's doing the same thing, but on the character level. So let's imagine a data set like this. Imagine a file like professors.txt. And you could have the names of DP, or the department professors, like Lucas, right? Maybe Tiago, Marcos, right? Ricardo, Sabrina, so on and so forth. Okay? So here's a new line, a new line, new line, new line. So you could list all the names of professors of the department. You could do this for the entire university if you want, or just pick all the names that you can find in Brazilian Portuguese and train a model to generate names. And the way you do it is just like every character here now is a vector. And your vocabulary is just all the letters in the alphabet, right? A, B, C, all the way up to Z. So this is 1, 1, 2, da, da, da. There's what, 26, right? I don't know, 24, 26. So then you can represent the character A with this vector, 1, 0, 0. And you just run the same model, but now on the character level. You predict the next character given the previous characters. Okay? This is what this network is doing. Okay. So if this text file here is something similar to this. So this is going to make a list of characters, right? It's going to make a set out of the data. So that's going to return all the letters and make it a list. So this chars here is your vocabulary, okay? And then just some data here, data size and vocabulary size. Vocabulary size is the length of the chars. And then here's going to make two dictionaries that is very useful for encoding and decoding word or characters as vectors and vice versa. So this char to index is converting a character to an index. So if you give the character A, it's going to return this vector for you, right? And that index to char is doing the opposite. If you give it that dictionary an index, let's say 2, it's going to return the letter B. Okay? So it's just a way to encode and decode letters as numbers. And here are hyperparameters. hidden size equals 200. Here, he's processing this document 25 characters at a time. Okay? Because he's assuming the file is probably like maybe a whole book, right, or something. Then chunks of 25 make sense. Okay? I guess we can see this Domkas. So you could get, for example, Domkas Murro from in a text file like this, and learn to generate text like Machado de Assis just by predicting the next character. Okay. And it's a really nice experiment to do. So here's the parameters initialization. See how there is only 3 matrices, the WX, WEdge, and WY. So this code is very useful for your assignment. You're going to build something very similar to this, okay? And 2 bias vectors, one for the hidden layer and one for the output layer. And here this function does the magic. So this computes the loss function, but it has inside it the forward pass. So the forward pass is right here. As you would imagine, this just implements the equations we saw on the slides, okay? So this is making one hot encoding. Actually, these 2 lines. These 2 lines are actually encoding the input t as a vector full of zeros and just one in one position. And this is actually the forward pass of the RNN, which are the 2 equations we know. Right? Tan age of np dot wx x plus np dot wedge, the hidden state plus b edge. And this is the output layer at the bottom. Okay? And this is softmax. Okay? This is the softmax compute is getting the probabilities from the output layer. And actually, this is softmax and this is loss. This, remember, I told you this is the sum, right, over t of minus log of the probability. So that's exactly the formula we had on the slide. So I actually made a simplification, so if you look at the slide and you look at this code, the equations should match. Anyways, and here is the backprop. This is the backward pass. It's initializing the gradients, dwx. For each of the weight matrices and bias vectors, we need a matrix, or we need to compute the gradients. Essentially, what we need at the end, right, is to know how to update these 3 weight matrices and those 2 bias vectors. So this, this, and this, and this, and this. So here is the backprop through time. It's actually running a for loop like on the reverse order of the input. Okay, so this is the equations we saw on the slides. Obviously, this is written in NumPy, but you should be able to make sense of this implementation and those equations. Okay. All right, and that's it. It's for training the whole network, and the rest is the training loop. Here, this is the training loop. Why true? It's a while true, but anyways. And here is the gradients, right? And here is gradient descent. Here's the update step of gradient descent. He's using AdaGrad, which it's a very similar to RMS prop. Yeah, there's no time to discuss every line, but one thing that I actually would like to talk about is this function of sampling. So once you train a language model, you could sample from it to generate new data. So assume we have learned this like probability of names. So what the language model gives to us is, as I already said, the probability of the token xt given xt minus 1, xt t minus 2 all the way down to x1. What you can do to generate new data is we can start with a given letter. Let's say L. And imagine if I've trained this not only on the data set of professors' names, but maybe like all the names in Brazilian Portuguese. Right? So if I start with this is an input, this is x1. So I'm going to use now my RNN, my language model, which is an RNN, to sample from the given probability of x2 given x1. And x1 is equal to L. So it should perhaps give very high probabilities to vowels, right? Because in Portuguese we normally don't have C in here, or D, or T, or any consonant. Normally after a consonant comes a vowel, right? So maybe here you would have, is there a name like start with Larissa, for instance, right? So yeah, it could be a very popular name. So A perhaps has 0.3 probability, and then A, B, C, D, E. The next is E, right? So maybe this Leonardo, right? So maybe this also has 30% probability. And I, O, U. So maybe all of them, right, have the same 0.2 probability because there is many names that start with L. Then I can just sample from this distribution to pick the next word. And here's the code to sample. But basically, I'm going to choose a character at random following this probability. All the other characters, B, C, D, E, they will have probably 0 probability. But they will be here actually in the distribution. So it's not uniform. But I would sample from this distribution, and maybe the next word would be I. Right? Is this clear what I'm doing? And you can implement this in the assignment, so you see this working. So you can print the values and understand the sampling approach. But maybe now I have x2 equal to I. I sample it, and by chance I got I. Okay? So now I'm going to concatenate that character in my previous input and run my RNN again. Right? Sorry, language model. RNN. And this is going to give me the probability now of x3 given x1, x2. Now this is L and this is I. So the only name that comes to my head is Leah, which would have A here. Maybe this would be 0.4, 5, 0.3. Anyways, you got the idea. But the model would give more probabilities to the characters that are more likely after that prefix. Okay? And that's how you can sample. You just keep, inferring from the language model. You start with a given character, you sample to get the next character, you concatenate it back to the input and repeat the process. You're going to get a third and concatenate back, and now every time you run the language model, your context is increasing, x3, x4, x5, x7, and so on. So you can stop after a certain number of iterations. Let's say I'm going to generate 100 tokens, right? But then this wouldn't be very smart, because then maybe you want your model to know when the name ends normally, right? So to teach that to your model, there's a trick. We can create special letters. Maybe you can use the letter at, or the character at, to denote end of name. And then you insert that character in your data set. Right after every name, you put the character at. And so the model will learn that after, for example, if you had by chance sampled Leah, since it's not very likely that there is a name that has a prefix Leah, maybe the more likely character now is actually end of name. So your language model is going to learn that after, for example, this context, it would give a very high likelihood, let's say 0.999 of end of name. And then if you're going to, even if you sample, you're going to have almost 100% chance of sampling the end of the character, and then you stop. Let me show you this. So this is also, so this blog post from Andre came out when he were working with RNNs back then, 2015, before, so this is prehistory now. This is before transformers, right? So at this time, at this point in time, this is the year I started my PhD. At this point in time, everyone was really excited about RNNs and like generating stuff with sequences. And then he wrote this blog post discussing that implementation. So this post comes after this code. Wait. So he was playing with this, and then he actually went out and put out this post, and here you can see my inspirations. But here, what is cool about this post, and it's called the unreasonable effectiveness of recurrent neural networks, because he was really surprised about what they were doing. So for instance, you can train an RNN to generate images. Back then, you could do that by learning a sequence of image patches. So here, if you look at the right, so on the left-hand side, these are the patches being processed from the top to bottom, from down to like left to right, top to bottom. So you're learning an image like this, and each patch is a token, right? And then you learn this distribution, and you can generate now images sequentially. See how like on the right here, you see this RNN actually producing new images. This was trained on pictures of address numbers on houses. Right? And here he's commenting that implementation. Okay, he's actually explaining RNNs and so on. And this is a like kind of example we saw on the slide. So let me show you a couple of cool results. So he trained the same way I mentioned. You can train this to generate Machado de Assis. He did this on Shakespeare. So he got all the works of Shakespeare as a text file. So the RNN generated this, and he learned the whole structure of the script or the text. He learned some words, like many words, like little, and, who, is, but, a, chain, and, subjects. So all these words were learned character by character. Okay, but it's obviously hard for an RNN to learn really, like, to form more long, or to combine these characters in a sentence and make sense of them. So it's when you read this text, when you look at it, it looks like English, but when you start reading it, there's many correct words, but the whole sentence doesn't make sense, right? Like, they are away these miseries produced upon my soul. And so here's Wikipedia, right? Same thing. But he trained this on the markup language of Wikipedia, not on the actual text. So Wikipedia, the documents of Wikipedia is actually written using a markdown language or some sort of like markup language. So he trained that RNN on these documents. And then the RNN learned the structure of the Wikipedia structure. So he could produce new documents formatting for Wikipedia. So he learned that you should have like have this section C also release. So he learned some categories to add links and so on and so forth. Okay. So it creates headings and footers and whatnot. So it's really interesting. It was trained on actual papers, right? Written in LaTeX, character by character, and all these you're seeing here is generated by an RNN. This is gibberish. This is like just generated text. But it looks like actually math papers or something, right? It has proofs in it, right? But it doesn't make any sense when you read it. Like this is a form. So this is form all shivers of sheaves on X, but given a scheme U and surjective et al. So morphism. So you see that it makes mistakes, and in the global level it doesn't make any sense, but locally it makes a lot of sense, right? And that's one characteristic of these simple RNNs. They are very good at what we call local dependencies, but they suffer to represent global dependencies, which is this kind of global context when you generate and when you model these things. So it's really tricky to model really large sequences. So just like more examples here, it trained that RNN on the Linux kernel. Back then, this is not ChatGPT or anything like that. This is a RNN, and that network learned to write C program, right? At least stuff that looks like C, right? So it learned to put types before function names and like to write arguments in parentheses. So he learned all of that by hand, like by training on the Linux kernel. He learned comments, right? If, else statements, go, choose, and so on. He learned all that, right? Opening, closing strings, putting semicolons, and whatnot. So even from back then, people already had an idea that these things could actually be used to generate code. And this kind of things we are seeing today has the same principle. So ChatGPT has the same principle, it's just more a much more efficient and bigger network. Okay. Okay, let's see if there's anything else that is cool. Generating baby names. Here are actually generated names. This is the kind of work we'll be doing in this. But let's move on because we have more stuff to talk about. Okay, so as I already mentioned, RNNs, they suffer from these exploding vanishing gradients, especially when they are dealing with long sequences. Because now backpropagation runs through time. So if I had, let's say, a sequence that is 1,000 characters long, I would have this chain rule with 1,000 multiplications. Okay, so the longer the sequence, the harder it is to flow the gradients now because I have to flow them back through time, through each input, each time step t. So just looking at the code, I think is easier to visualize. If you want to look at the diagram here, it's up to you. But so here you see the general diagram of the RNN going from time step 1 to time step t. And the same thing here you see in code at line 48. That's the for loop over the time steps, okay? And the red arrows, these are the gradients flowing back. So think about this very first time step 1 here. If my sequence had 1,000 time steps, that for loop would run 1,000 times, okay? And just so you get a better intuition of what's going on, if you look at line 58, this line is multiplying this matrix W edge by this variable W edge raw. But if you look up here, this variable W edge raw is using D edge, and D edge is using D edge next. Okay? So what's happening here, if you look at lines 53 and 58, you're going to see that what you're doing is actually multiplying WH by itself many, many times. Okay? And then it's easy to argue that if you have values in that matrices that are greater than 1, very quickly you're going to have these exploding gradients because they're going to start growing. If it's a 1.5 times 1.5, so they're going to grow exponentially. Okay? And the same with for vanishing gradients if the values of this matrix is less than 1. Okay? So you're multiplying, just think about this, right? If you're multiplying 0.1 times 0.1 times 0.1 1,000 times, this is going to very quickly get close to 0. And this is what happens here. So to solve these problems, researchers have came up with different types of RNNs. And there were many different subtle variations, but there are two of them that became more popular. Long short-term memory network, or LSTM for short. You can see LSTM as a more complex RNN, but the way they operate is the same. They take an input at each time step t, and they produce an output at each time step t. They just produce that output in a different way. Okay? So let's just compare. This is our simple RNN, right? So now I'm showing this diagram here where each of those green boxes, they are one time step, right? And I'm showing kind of this circuit type of visualization to illustrate these equations of the classic RNN. And LSTM is just a more fancy, complicated set of equations. Okay? So I put them all at once so you get scared. Oh, whoa, wait, what's going on, right? And this is the circuit. Right? So this is the flow of information on an LSTM. Let's see each one of them, or piece by piece. First of all, let's just remind ourselves that in a classic RNN, we have one hidden state, edge t, that is produced by combining the hidden state of the previous time step and the current input xt. What the LSTM does is it has this kind of idea of what they call gates. Okay? And you'll see that in action right now. So let's go slowly. First of all, this is the first equation there. Okay? So let me show ft. The very first equation in that set of equations is what we call the forget gate. Is highlighted there. So the forget gate is going to concatenate ht minus 1 and xt. Again, this is just a compact format of writing those two sums. Okay, this is just merging two matrices in one matrix. Okay. So the forget gate has this WF matrix. This is a weight matrix you're going to learn when you train the model, where you're going to multiply by, again, the input xt and the previous hidden state, okay, and sum with another bias term. And the purpose of this forget gate, as its name suggests, is to forget information from the sequence. So the LSTM has this idea of like deciding at each time step information that it should forget and information that it should include in this current state. Okay? So this, at the end, this is a sigmoid, right? So ft is going to be a vector with values from 0 to 1. Okay, so this is going to be, it's a sigmoid. So ft would have values that goes from 0 to 1. So now we have the input gate, which, just look at the very first equation, is exactly the same as the forget gate. It's just a new set of weights, wi. They are multiplied by the same thing, hidden state t minus 1, concatenated with x, and there is another bias term bi. So it is the input gate, and the idea here is that we want to bring new information to the state. Okay? And what is this state? Now we have what we call a C state. And we use this tilde mark there to indicate that this C tilde is a candidate state. So we're going to produce what we call like a possible candidate to be my future state. And again, this is the same thing, edge C multiplied by edge t minus 1 xt plus bc. But now we are using a tan edge, okay? And if you want to really understand why they are, so the sigmoid here is there because I want these values to be from 0 to 1. This state, the tan edge is here because it helps flowing the gradients to the tan edge. So here is a nonlinearity that back then was a good choice for learning large sequences. So this is not because of the value boundaries. This is more to add nonlinearity to the game, but but helping the network to learn longer sequences because it's easier to flow the gradients through a tan edge. And if you look at if you want to look at the original paper, this is the paper. Okay, so it's from 1997. And there they're going to discuss this question. But then at the very end, you have this CT, which is your update. Here you're updating your C state. You can see the C here variable as a vector. It's similar to the hidden state that we had before in the classic RNN. But this C state here, it's flowing kind of through the hidden layer without much like computation. So this CT is a result of multiplying CT minus 1, which is the previous C state, okay, times the forget gate plus the input gate times the candidate. So think about this. This is a weighted sum, okay? So my new state is a combination of what I want to forget from the previous state, ft times ct minus 1, plus what I want to include from my candidate. So it is like weights, so these are 0 and 1, right? These values are from 0 to 1, these values go from 0 to 1, so they are weights. And this is a vector that is my next, is bringing information that I want to include in my state. And this is my previous state. So pretty much what this equation is doing is using this learned vector to control how much I want to include versus how much I want to remove from my previous state. And here's my previous state and here's my new state. And then that was it. And then now we can produce an output. So there's two states now. There is the hidden state and there is the C state. So both of them are flowing. See, there's one at the bottom, one at the top. Both of them are flowing over time. In practice, what normally we use to generate the output y hat is also the hidden state. So I'm not showing the equation of y hat here, but you could just use this edge t to produce an y hat if you wanted. Okay? But basically, this OT is also a sigmoid which controls, which generates or updates HT based on CT now. And well, this is all complicated, looks very kind of math heavy, but it is based on this idea of remembering and bringing information to the state. But what I want to show you, like the main takeaway is this C state that has only 2 nodes in its computational graph. So the sequence can be very, very large, and you're just passing this through one multiplication and one summation to produce C. And that makes the gradient flow much easier through that C state. So this really helps learning larger sequences. It's similar to residual networks. Because in residual networks, you also like kept some connections to make the gradient flow easier. And here is the same intuition. You're reducing the amount of computation over time. Look, these are still complicated, but at the end of the day, when you actually now compute the how do you call, the partial derivatives of the C state, now you'll see that you won't suffer of those, like have many of those like series of multiplications as much as you had from before. Okay, so I just want to mention, you don't have to worry about this. There is another version that is very popular called GRU, which is just a different type of LSTM. It's actually simpler than an LSTM. It has only 4 equations. So the GRU is actually a simplification of the LSTM. Because people were debating, like, what is actually making this thing work? Like, do we actually need all these gates? And then people were experimenting with these ideas. And then he simplified this and boiled it down to 2 gates, right, Z and R. And then here, what you have is just ZT is you're learning just one weight. Instead of learning 2, instead of having a forget gate and an input gate, you're going to have just one weight, ZT, which is here, right? So ZT here, instead of learning like the forget gate, you just learn the input gate, and the forget gate is 1 minus the input. So you removed one gate right away, okay? This edge T here follows that idea of forgetting and inputting new information. Now I'm just using the candidate edge tilde T. So this candidate edge tilde is very similar to the C tilde, which is information I'm going to bring in the sequence. Okay? They have the same intuition, just different structure. And again, if you look at the edge state up there, it's flowing more easily right now through this formulation. Okay? And it's really hard to debate which one is better. To be honest, like at some point people will realize, okay, these apparently are the same. And GRUs later in history started to become more popular because they're simpler and they just work as well as LSTMs. Okay. And if you want to read the paper, this is by Joshua Bengio students. There's just too much to talk about. I'm just going to briefly mention this, guys. You can also do bidirectional RNN. You can have an RNN that processes the sequence from left to right, and just have another completely different RNN that processes the sequence from right to left. And then at each time steps, you concatenate the hidden states to produce the output. Okay? See here, this arrows here, you can see this as hidden state concatenation. So you have the hidden state from the left and the hidden state from the right. So you have the context from the left and the context from the right at each time step. But to make this work, you have to do this from left to right, then from right to left, then you can concatenate, right? Because you need both of them, the whole sequence completed to be able to do this. You can't do this one step at a time, both sides, right? You have to do first left, and then do right, and then you concatenate everything, and then you do your output. So this is very useful for, let's say, named entity recognition, because this way now, for example, when you look at those 2 sentences, teddy bears are on sale and Teddy Roosevelt was a great president, right? If you were modeling this sequence from left to right, after looking at the word Teddy, you wouldn't know that this was referring to teddy bears or the president. But if you had another LSTM or RNN or any type of RNN flowing from the right to the left, by joining these 2 states, hidden states, you could now have context from left to right and right to left. You would know. You know that now you have president at the end in one sentence and sale at the end of the second sentence. Unfortunately, we don't have much time. If you guys are interested about this, we can maybe try to find another time to bring more discussion of RNNs. There's a lot of cool ideas here, okay? Yeah, sorry about the delay. Next lecture, we're going to move to word embeddings, which is this idea of modeling words with vectors. Thank you.